and welcome to Geeks for Geeks. In this video, we would be discussing the solution of the problem minimum element in a sorted rotated array. So, in this problem, we are given an array of distinct elements. So, what do we mean by distinct elements? Suppose we have 1, 1, and then 2, 3, then this is not valid. And if we have 1, 2, 3, then this is a valid input. Why do we mean by this? This means that each element should have a frequency 1. If it has a frequency more than 1, then it won't have distinct elements. So which is initially sorted. So initially it would be sorted. Suppose we have 1, we have 2, we have 3, we have 4, we have 6, we have 5, we have 6, we have 7, we have 8, we have 9, and we have 10 itself. So now if we rotate the first element and take it to the last, then this would be removing this element, adding it to the back, and removing the arrow also. This is the rotated array. And the minimum element in this array is 1 itself. So now as we can see that the brute force approach to this problem is to consider all elements, consider each element itself. After we are done with the consideration of each element, we need to find the minimum out of it. After we have taken out the minimum, we need to return it. So this seems quite simple. So now there are few other things to understand too. Suppose we have 1, we have 2, and we have 3. So now we need to find the minimum element. So the minimum element can be 0 also. The minimum element can be 1 also, any number. So now it entirely depends on the input type. So what we need to do is we need to initialize a variable, anything. You can name it anything. Here I am naming it as x to make it simple. You can initialize it with the maximum number. Why with the maximum number? Here we can, if the input type is int, we can just take int max. Why are we doing this? Basically, if suppose we take just 10, then and the input x value is equals to 10 and the input is 100, 1000 and 2000, then this x won't be able to figure out the minimum element. That is why to solve this issue, what we do is we initialize the minimum value with the maximum value so that howsoever big the minimum value is, we would be able to have it. And then we would iterate and compare at each step. Okay, now let us start the implementation itself. So we can have A, and I would name it as with L and H itself. Now we go down. Now what we do is we initialize int mn is equals to int max, which would store the minimum element. Now what we would do is we would iterate on the array itself. We would have used for each loop, but as we are given a range and we need to find the minimum element within the range, so for each loop would bring us a wrong value. So we would move forward with int I is equals to L, I is less than equal to H, and I plus plus. Okay, we would go from L to H itself. Now, if A of I is less than Mn, then we would update Mn. Mn is equals to A of I. And then we would simply return this Mn. Simple enough. Now we would just run this. Okay. Now let us submit this. And yes, we got an AC. Okay. Now there is one more simpler implementation of this if statement. What we can do is we can have something like mn is equals to min of mn and a of I. So this would take out the min and we are assigning again to the mn. This is just an alternative to the last if statement, and this is the use of STL itself. So let us now see the time complexity of the solution. So if the array A has n elements and we need to iterate over all the elements to find the n elements, the time complexity of this approach is big O of n, and the space complexity of this approach is big O of 1 itself. Fair enough? Now, can we do better than this or not? So let us see. Now, what are the informations we are given? The informations we are given are the array is sorted, then it is rotated. Okay, the array is sorted and then it is rotated. So now let us try to think how we can find the minimum element. So we can think of that if the array is only sorted, then the first element would be the minimum element. We know that. Now, if the array is sorted and then rotated, that means that the array, the element, so suppose we have A1, A2, A3, A4, and A5 itself. Now, the position of the minimum element can be in the first position, that it is not rotated, can be at the middle position, or can be at the last. These are the only three positions. Either it would lie in between, either it would lie in the end, either it would lie in the front. So if it is lying in the front, then it is very easy that we would just simply check. But suppose the last element. So let us first take the scenario when it is rotated and it is in the middle. Suppose we have in the middle, so we just write 1, 2, 3, and here we would write 4 and 5. Okay, this array is also rotated with the minimum element in between. So now let us try to find a relationship between this. So what we can do is we can see that at this position we have this element as small, we have this element as small. Okay, at this position we have the next element as large and the previous element as also large. So let us check the uniqueness of this. Is this valid for this case also? No. The next element is large and this element is small itself. So if both the element are large, okay, on both sides, and it would be definitely large for the minimum element. Why I am saying you this? Because just before the minimum element, maximum element would lie there, and just after the minimum element, if it is rotated to some point and if it is in between, then after that it would be sorted. So definitely the next element would be greater than that because it is distinct elements. एक बार फिर से इसको हिंदी में समझते हैं, ट्रांसलेटिंग द सेम इन हिंदी. सपोज जो मिनिमम एलिमेंट रहेगा उसके आगे वाला एलिमेंट तो रोटेटेड एरे का लास्ट एलिमेंट होगा, तो सॉर्टेड एलिमेंट का लास्ट एलिमेंट तो सबसे बड़ा होगा. सो डेफिनेटली मिनिमम एलिमेंट के इस तरफ वाला बड़ा तो होगा ही. लेट अस सी फॉर दिस. अगर वो रोटेट हुआ है और वो बीच में है तो उसका अगला वाला एलिमेंट तो डेफिनेटली बड़ा है क्योंकि वो सॉर्टेड है. दैट वी वुड टेक द एडवांटेज ऑफ दिस. सो फॉर मिनिमम एलिमेंट a of I minus 1 is greater than a of I, and a of I plus 1 is also greater than a of I. Both the condition are absolutely true itself. Okay, now we can say that if we iterate on all the elements and if the element is in between, we can find out. But still the time complexity is big of 1 because we need to iterate on all the elements except the first and the last element. Okay, why not first and the last element? Because if we iterate on the first and the last element and we try to access the index I minus 1 or I plus 1, then it would definitely give us an array out of bounds. Okay, fair enough. That is why they need to do this. Then we come to the last element. Okay, so we can say that if we are at this index, okay, if we are at this index, then we would simply see the last element. If the last element is less than this, that means that कुछ तो उधर से रोटेटेड है और इस तरफ तो अभी बढ़ा आ रहा. That means वो मिनिमम एलिमेंट इस तरफ होगा, राइट हैंड साइड, नॉट लेफ्ट हैंड साइड. इस तरफ जाएंगे तो एलिमेंट का वैल्यू कम होगा, पर रोटेशन के बाद का एलिमेंट उधर ही कम है. Okay, translating the same in English is, suppose we find that the current value is greater than the last value, then definitely even if we go this side, then we would get an element which is greater than the last element. So there is no point in going there. So definitely we would need to go on this side. And this gives us an idea that we need to use binary search here. Why binary search? There are two reasons for thinking that this should be used. Because we have solved this problem in big O of n. And this is a sorted array. So if we want to perform better in searching an element in a sorted array, even with a little modification, we should think of an element known algorithm known as binary search. Because sorted element hai, the array is sorted. The next thing is that we need to perform better than big O of n. That is why we would move forward with binary search itself. Okay. The next reason is that this is a monotonous function, because if we are here, we can know that we need to go on which side, this side or this side. Monotonous function basically means that if it satisfied a particular trend, suppose like this, or like this, or like this, or like this, it can't be 1010 or 10110. It can't be like this. If this is the scenario, these things are not valid. If this is the scenario, these things are valid itself. Okay. Now, how to use binary search here? So, we can initialize the we can initialize the minimum element to the positions at this side and this side. Then we can search the element. But before that, we need to consider for three cases. If it is at index 0, if it is at the last index n minus 1, and if it is from 1 to n minus 2. Okay. So if it is at the 0th position, we would see how can we do it. Okay. If it is at the n minus 1th position, then it is very simple. If we just check that the last element is greater, we would just do it. Now let us move to the implementation, and I would explain you in detail how to use binary search here. Okay. I would remove the initial things and I would make sure the other things are same itself. Now, before we start the implementation, let us first handle the case when there is only one element. Why we are handling the case when there is only one element? Because if there is only one element, we don't need to process anything. Okay, so this is just like the question of anagram, that if the length is not same of both the strings, then we would simply say no. So we would do the same kind of like that. So if L is equals to H, that means we have only one element, then we would simply return A of low or A of high. We can return either of them. Now, the second scenario, when the last element is the maximum element. So if we have the last element as the maximum element, so suppose we have like this 2, 3, 4, 1, 2, 3 itself. Okay. If we have something like 4, 5, 6, and then 1, 2, 3. If this is the rotated array, then the last element, this element would be less than this. But if it is not rotated and the minimum element is at the end, If the minimum element is at the end, then we have something like 2, 3, 4, 5, and then we have 1. So definitely a of high minus 1 is greater than a of h. So we would return a of h. So if a of high is less than a of high minus 1, then we would return simply the last one, the last element. Now what we would do is we would have the low as L plus 1 because we would compare only the middle elements. So we would have low is equals to L plus 1, and then high is equals to H minus 1 itself. Now we have the high minus 1 because we would also evaluate the middle elements. Now we would move forward and we would do the same of binary search syntax. If low is less than equal to high itself, then we would take out the mid is equals to low plus high divided by 2. Now we would check the condition for this. So we have already wrote the condition that if a of mid is less than a of mid plus 1, and same goes for minus 1, a of mid is less than a of mid minus 1, because we saw that this would be valid only for the minimum element. So we would return a of mid itself. Okay, now we go down. Okay, now if a of mid is greater than a of h, that is the last element is greater than that. So if the last element is greater, so let us suppose the last middle value we are now doing is greater. Suppose we have 4, 5 and 6, and we have 1, 2 and 3. So if we are at this value, then this value, if it is greater than this value, that means that we need to go on this side. Why? Because the minimum element won't ever lie on this side. Because if we go on this side, then this would be less. If we go beyond that, this would be greater. So if it is greater, we would need to go on the right hand side. So if we want to go on the right hand side, we would make low is equals to mid plus 1. Else what we would do is high is equals to mid minus 1. We would do the opposite. Okay, because we saw that in this side this would be less, in this side it would be more. And if these all conditions, if we are not able to find, so we have already checked the condition for the last element, middle element is also processed. Now the only remaining condition is the first element. What we would do is we would simply return a of L itself. Okay, let us compile and run and let us see if we can get. Okay, and yes, we got an AC. Now let us try to evaluate the space complexity and the time complexity. Let us first do it for time complexity. This is just checking is equals to. So operators take big O of 1. This is also big O of 1. This is the binary search, and this comparison for each bind. So we would be doing log n operation, and for each log n operation we are just checking using operators. So for each log n operation we are doing big O of 1. So the upper bound to this is log n. So the time complexity of this approach is log n itself, which is the expected time complexity. Let us talk about the space complexity. We have only used the low, high and mid to initialize or to keep the values. We have not used any auxiliary space. So be it whatever number of variables we initialize, it would be constant. That is why the space complexity to this solution is constant. So that's it for today. Thank you and have a nice day.